All right, AP Calc, we're going to move on now into the last part of our notes right here for section 5.1. And if I'm remembering this correctly, I think that your textbook actually pushes off this concept, the trapezoidal approximation method, until later in chapter 5, which always seems weird to me. What we've been doing so far in section 5.1 is talking about approximating the area underneath a curve by dividing that region up into certain types of rectangles and then finding the area of each rectangle and adding them all together. Now, the trapezoidal approximation method is another way of coming up with an approximation. Notice that word shows up here again, an approximation for the area under a curve, and I just don't see the logic to having all this conversation about approximations with rectangles and then not diving into trapezoids while we're here. So here's what we're going to talk about here, guys. First thing I want to make sure everybody has down in their notes is the formula right here for the area of a trapezoid. 1/2 times its height and then times the sum of its bases. Now, one thing that's going to be a little bit interesting here, guys, is that most of the time when you drew a trapezoid, maybe back in geometry, you probably drew it in this general orientation right over here. Now, the definition of a trapezoid, if you'll recall, is a four-sided figure, which is a quadrilateral with exactly one pair of parallel sides. So almost every time that you drew a trapezoid back then, it was the top side and the bottom side that were parallel to each other. Those two sides right there are called the bases. So this would be base 1 on top, and this would be base 2 on bottom. The other two sides, which are not parallel to each other, are called the legs of your trapezoid. But you'll notice those don't factor into the formula for area at all. The height of the trapezoid would be measured perpendicular, actually, to both of the two bases right there. So that would be your height right there. Another thing I want to point out is that this way that I've drawn the trapezoid is the way that most people think that it has to be, but I've actually drawn a specific type of trapezoid here called an isosceles trapezoid because it looks more or less in my diagram that the two legs are congruent to each other. That certainly can happen, but it doesn't need to happen. So you could have a trapezoid that is drawn like this, okay, or maybe a trapezoid drawn like this, where one of the two legs is at a much sharper angle than the other one right here. So in both of these two cases that I've just drawn here at the bottom, these are trapezoids, because they're quadrilaterals with one pair of parallel sides, but it looks like the two legs are not congruent to each other. So don't make the mistake of thinking that every trapezoid has to be isosceles. Okay, so with all that in mind, I'm actually going to erase all that because I need this space right here. Let's start talking about a little bit of a problem with everything that we've done so far here in section 5.1. We've been trying to approximate the area underneath a curve by drawing rectangles. So let me focus right here, guys, on subinterval number 2, the one that starts at x sub 1 and ends right over here at x sub 2. And up until this point, we've been talking about drawing rectangles here with a little bit of an issue right here. If I were to draw a left endpoint rectangle on this subinterval, I would go from the left endpoint right here, which is x sub 1, and that would determine the height of that rectangle. So what I have in red right there would be the left endpoint approximation. The problem with that is that this approximation on this particular curve, on this particular subinterval, is too high because it gives me this extra area right here that isn't actually contained under the curve. So I can look at this quickly and see that at least on this subinterval, that left-hand approximation is going to be too high. So what else have we learned? We also learned how to do a right endpoint rectangle. So I would go from the right endpoint here at x sub 2. That becomes the height of this rectangle, okay? And now that would be our right endpoint approximation. The problem here, this approximation is going to be too low because I'm missing all of this area right here that is under the curve that I should be counting. So obviously left and right rectangles, there's some imperfection involved in those methods right there. A third thing that we learned, kind of a compromise, would be the midpoint rectangle right here in the middle. And if I went up there, okay, and this is what my rectangle would look like, and there you go. And as I said, this is kind of a compromise. Here I'm missing area right here that I should be counting, but I'm also counting area right here that I shouldn't. So that midpoint approximation seems like a decent compromise between the other two. But what if, let's think outside the box here, everybody, that's kind of a pun, what if there were a better way to fit a polygon underneath that curve that didn't involve rectangles. So what we're going to do instead is we're going to use both this left height right here, so evaluating this function at x sub 1, and the right endpoint right here, evaluating it at x sub 2, and rather than trying to make a rectangle out of this, what if we actually just connected those two endpoints right there and created a new shape right here, which would be, wait for it, since this left side was vertical and this right side was vertical, those pieces have to be parallel, and now we have ourselves a trapezoid. Now, obviously, that trapezoid isn't perfect either. It looks like in this case that trapezoidal approximation is going to be just a little bit too big because I'm counting area that's actually above the curve. But if I were to continue that idea of drawing this thing, okay, I could draw a trapezoid right there that looks like it might be a little bit too low. A third trapezoid right over here, looks like maybe it would be just a smidge too high. And then maybe this fourth trapezoid, I'll go ahead and draw there as well. Now if we take a look at that, guys, if we were to take the areas of our 1, 2, 3, okay, and in this example I've drawn 4 trapezoids, but in reality it's whatever the value of n is. You've drawn n trapezoids here. That actually looks like it would be a pretty decent approximation for the area under the curve, and maybe even better than any of the 3 rectangular approximations that we've come up with so far. So this is a little bit interesting, but let's talk about how it is that we are going to do this. All right, so our general formula, we're going to write this really big and put a big box around it here, guys, would be that a trapezoidal approximation, so t sub n, is going to work on this. Now, what we're going to do, I'm going to go ahead here and just kind of cut right to the chase here. Every one of these trapezoids is going to have an area that follows this formula right over here. And so every one of them is going to have a 1/2 out in front, and every one of them, this is a little interesting now, is going to have the same height. But I got to go back and remind you of something we wrote a second ago. Most trapezoids you saw back in geometry were drawn horizontally, meaning that it's the horizontal segments that were parallel, and that makes the height vertical. But let's ignore that now, guys, because the trapezoids we're going to deal with here are running the opposite direction. Now, it is the vertical pieces here on the left and the right that are parallel to each other, which means that the height is actually running horizontally here between those two bases. And that measurement right there we have also used in other sections here earlier, and we've called that delta x. So the height of your trapezoids is delta x. And in most of the problems that we're going to see, that height is going to end up being consistent. It's going to be the same on every one of these trapezoids if we're dealing with regular subintervals. So I bring all that up to say that we can bring out the 1/2 and then the height, which is the delta x, and we can bring that all the way in front of this formula and then start a big set of brackets. Okay, so what's going on right here? What we need to do is in the first trapezoid right here, we need to add up its two bases. Well, base 1 now is going to be this height over here on the left, and base 2 is going to be this height on the right. Well, that height on the left comes from evaluating f at x naught. And then we'll add to that base 2, which is going to be f evaluated at x sub 1. And what I have right there, guys, is the sum of the bases for trapezoid number 1 right here. But now as we move on to trapezoid number 2, again, this 1/2 and this delta x were pulled out because they're constant. I just now need to add the two bases of trapezoid number 2. So its left base, this one right here, is again f of x1. So that's interesting, guys. The f of x1 shows up twice, and the reason why is because this vertical piece right here is both the right base of trapezoid number 1, and it's also the left base of trapezoid number 2. And then we'll add to that the right base of trapezoid number 2 right here, which anyway, that one is going to be f of x sub 2. And now maybe you can see what's going on here, guys. So there are the two bases of the first trapezoid. Here are the first two bases of the second trapezoid. The third one would begin where the last one left off. That would be f of x sub 2 plus f of x sub 3. And I'm going to put a plus now, and I got to jump down to the bottom, a dot, 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 because this is going to continue now for a while. And we're going to end up then with, let's take a look right here. I'm going to go to this fourth trapezoid, but really I should be calling that the nth trapezoid right here. And if this piece is generically called x sub n, I really shouldn't be calling this x sub 3. I should be calling this x sub n minus 1. We're one short of the last one here. So for our last trapezoid, its left-hand base, this piece right over here, is going to be f of x sub n minus 1, and we'll add that to its right base, this piece right over here, which is f of x sub n. And that'll be the last piece right here that we're adding together. So, lucky for us, everybody, that formula can be cleaned up just a tiny little bit. So if you give me a second, I'm going to shrink this down here. I might move what we did here just a little bit. We'll go ahead and we'll finish the formula right there where we had room to do it. Okay, so, well, that's not what I meant to happen. All right, give me that. All right, so we can clean this up just a tiny bit, although I got to tell you, this formula is still messy. This is the one, guys, I lied before, sorry, that we're going to put in a box. So every trapezoid has a 1/2 because of this part of the formula and the same height, assuming that the subintervals are regular, delta x. And now in brackets, what I want everybody to notice is that f of x naught only shows up once here. So we're going to write f of x naught, and that's it for that. But f of x sub 1 happens twice, as we said, because it's the right endpoint of the first trapezoid and it's the left endpoint of the second trapezoid. And likewise, f of x2 is going to occur twice. And same thing with f of x3, and same thing with every x value up until the very last one. So because all of those occur twice, we're going to put a 2 here times f of x1, and another 2 times f of x2, plus dot, dot, dot. And then let me finish this thing up on the bottom right here, plus the last term that's going to get a 2 in front of it is not this height over here on the right, not this guy, but it's this one right here, the one prior to the last, the penultimate. That'll be the last one with a coefficient of 2. So it'll be plus 2 times f of x sub n minus 1. That's the last one that gets a 2 on it. And then the very rightmost point right there only gets used once. So that'll be f of x sub n, and that'll close that off. So that is certainly not a nice, clean, easy formula, guys, not by any stretch, but that's the way that this trapezoidal approximation formula is going to work. So we're cutting our region up now into trapezoids rather than into rectangles, and that gives us a pretty decent approximation as well. All right, so let's see that formula in action, guys. Now, just because I want you to get some context to what we're doing, we're going to do the exact same problem again that we've already done 3 different times. We've used, let's see, the left endpoint approximation method, the right endpoint approximation method, and the midpoint approximation method on this function, f of x equals x squared, on this interval from 0 to 3 with this step size, delta x is equaling 1/2. We're going to do it again, except now we're going to do trapezoids. Now, nothing has changed. With the same overall width right here of 0 to 3 and the same delta x of 1/2, we're still dealing with an n value of 6. Now, heretofore, I've always said that means we're going to make 6 rectangles. Now, it means we're going to make 6 trapezoids. But I'm hoping by this point, guys, you're starting to feel a little more comfortable with what we're doing. I'm going to not draw this one out, and I'm going to go ahead and just dive into the formula that we just wrote out. So T6 is going to equal, and here we go. Because the formula for the area of every trapezoid starts with a 1/2, you've got to remember to pull a 1/2 out in front. But the weird thing is, guys, we have a 1/2 right here, but then also that gets multiplied by delta x. And in this problem, delta x is equal to 1/2 as well. So just a coincidence here, but we're going to have 2 1/2s out in front of this big set of brackets. Now let me be clear, this number right here will always be 1/2. This number, though, is going to be whatever delta x is. So if delta x was 1/4, this would be a 1/4, but this first factor will always be a 1/2. Okay, then what happens inside the brackets, guys? We start off evaluating the function just once at x0, and x0 is the same as your a value, which is going to be 0. Then we start putting a 2 in front of all of these y values here. 2 f of, and then x sub 1 is going to be whatever your a value was right here, plus your delta x value of 1/2. So that'll be a 2f of 1/2. And then we keep going with the 2's, adding delta x each step along the way. So 1/2 plus this delta x means we're now at 2f of 1. Plus, okay, and I think we get it now, dot, 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 and then I'm going to finish it up down here. So we'll go plus. The last one that gets a 2 is going to be, let's go back and check this again, guys. It is going to be delta x less than this value right over here, your b value. So the last one that's getting used twice would be 2.5, or I'll just write that as a 5/2. And then at the very end now, the right endpoint's height only gets used once. So f of 3. So unlike the left endpoint approximation and the right endpoint approximation with rectangles, we're using both your a value here and your b value in our calculation right here for the trapezoidal approximation. But those guys only get used once. Okay, now that's a little bit of a mess, guys, but we've been working through this here. We're going to go ahead and go to the calculator now and see if we can get this to work out. And if I'm not mistaken, nothing's changed. I think I still have everything defined in my calculator. So let's go ahead and get started. We've got a 1/2 out in front multiplied by another 1/2 times, and now we need a set of parentheses or brackets, so here we go, and this will be a little bit tedious, but I think we'll get by. So what are we doing here, guys? f1 at 0, gotcha, and then we're going to add to that. This is where you got to start putting 2's in there. So it would be 2 f1 of 0.5, gotcha, plus 2, and we'll do f1 of 1. And by the way, while I'm typing this in, if you're getting a little bit bored with this, if you're thinking, boy, this has taken a really long time to type in, and I wish there was a faster way to do it, funny you should say that, everybody, because we're going to start working on that in class in kind of a shortcut method for how to do this. And I think I alluded to it a little bit earlier. We're going to start doing sigmas here, everybody, but I think I'll save that for another time and another video here. So, oops, I forgot a 2 there. See, this is what happens when you talk while you're doing this. So 2f1 of 2, gotcha, and then a plus 2 f1 of 2.5. Now that was the last one we were doing a 2 with, so now it's just going to be plus f1 of 3. Now I'm hoping here for an answer that's somewhat in the neighborhood of what we've been dealing with before. Some of the answers I've come up with, in fact, let's just scroll up and see some of them here, right, guys? I think that our first approximation, the left, was 6.875. We thought that was too low. The right endpoint approximation, 11.375, was probably too high. Then we did a midpoint approximation and got 8.9375. I think we averaged our left and right at one point and got 9.125. So I'm hoping for something that's somewhere in the neighborhood of those values here, 9.125. You'll notice that is exactly the same as what I have on the line above, the average of the left and the right. That actually comes down to what you're actually doing in the formula for area of a trapezoid. I'll maybe try to explain that a little bit later. But 9.125 is the answer that we've come up with right here. So 9.125, that's 9 1/8 square units, is our approximation right here for t sub 6. Now, later on in this chapter, we're going to actually come back and answer this question about what the real answer really is, but I'm going to leave you guys in suspense. We've come up with 4 different approximations, and so, since they're all, kind of in the same ballpark, we can start to say that the answer is probably somewhere in this neighborhood of around 9. Hint, hint, wink, wink, nudge, nudge. All right, I did want to do one goofy example with you here as well. We're going to find T3 in this problem. Now, please note, everybody, we are not just doing the same trapezoidal approximation with f of x is equal to x squared that we did right here. In this one, I've given you a whole new function. In fact, I should have been smart about that and called that maybe g of x or something different. But I actually wanted to go back to the very first thing we did in this section of notes right here, guys, when we were doing irregular subintervals. And when you're dealing with irregular subintervals, there's not really these nice fancy formulas here where you can just pull common factors out. When you're on to irregular subintervals, it's kind of every man for himself, so to speak. So what we have right here is some undefined function, g of x, or at least it's not explicitly defined. I'm never telling you, hey, g of x is equal to 5x cubed minus cosine of x. I'm not giving you that right here. All I'm giving you is selected y values. And what we're supposed to do is use this table to figure out T3, the approximation for the area underneath this G curve, starting at 0 and ending at 10 with these data points given to us. Now again, get in this habit, guys. How many points were we given? 1, 2, 3, and 4. That creates 3 subintervals. That's why. So, using that formula right now, a slight variation on that from what I did before, you can't really pull out the delta x because delta x is different each step along the way. From 0 to 3, delta x is 3. But then in the next one I gave you, delta x is equal to 1, and at the end there, delta x is equal to 6. So you can't pull out a delta x in front of this formula if delta x is different each step along the way. You can only pull out a common factor, which you have when we're dealing with regular subintervals, but you don't have when we're dealing with irregular subintervals. So at this point, guys, I'm not even going to pull out the 1/2, which I could do. I'm going to just find the formula of each trapezoid individually. So here we go. For the first trapezoid, its formula is going to be 1/2 times its delta x value. That's actually its height, which is 3, and then we multiply it by the sum of its 2 bases. And those 2 bases are going to be this 3 and this 13 added together. And you certainly could do that in your head and just write a 16 down there, but I'm trying to make a point here. I want you guys to see it in a second. Okay, everybody, that expression right there is the area of trapezoid number 1. And since we're doing 3 trapezoids, I've got 2 more to go. The second trapezoid always starts with a 1/2. Its height, its delta x, is 1. We're just going from 3 to 4, and its 2 bases are going to be 13 and 18 added together there. Got it. And then the third and final trapezoid, 1/2, its height is its delta x value, which is 6 right here, and its 2 bases are going to be 18 and 9 added together here as well. So let me stress this again, and you might want to put this in your notes, everybody. If you're dealing with regular subintervals, then a formula like the one that we came up with right here makes some sense. In fact, you might even want to write down this formula here really only works for regular subintervals. But once we get to irregular subintervals like this one right here, forget your formulas and just go trapezoid by trapezoid or rectangle by rectangle, and don't worry too much about a formula. This is a mistake a lot of my students have made in the past, which might be a mistake in the way I'm teaching it. The formulas really only work for regular subintervals. All right, guys, I don't know. I was hoping I could do this without a calculator. Let's see what we got. 3 and 13 is 16, which is even. Thank you. Half of 16 is 8. 8 times 3 is 24 for the area of that first trapezoid. Now I ran out of luck here. 13 and 18 is 31 times, yeah, that's odd right there. So half of 31 is going to be a 15.5. All right. And then here, 18 and 9 is 27. But I tell you what, half of 6 is 3. 3 times 27 is going to be an 81 there. All right, so what have I done here? 24 and 81 is 105. 105 plus 15 is 120, and there's a 0.5 at the end tagging along right there. So 120.5 square units would be our approximation here. I really have no way to test that value to find out if it's realistic or not, so we're just going to assume that everything worked out hunky-dory. All right, guys, that's kind of how we do trapezoidal approximations. There is one more thing that I wanted to do with you here, and I left this slide off of the previous video that we were doing with rectangles, but I want to go ahead and hit this concept as well as this concept right here. Are our approximations too high or too low? And wanted to talk about really figuring out which is the case here. So I talk here about the 4 possible cases of drawing a rectangular approximation here, guys, and trying to figure out what's going on. So if we take a look here, guys, the first curve that I've got right here, I'll call this curve number 1, is increasing at an increasing rate. And on this one subinterval that I've created with my 2 green dots, my left approximation right here looks like it's going to be too low. So I'm going to write that one down. My left is too low, but my right approximation, I'm just going to draw this right over the other one right here, my right hand approximation is going to be too high. So if that's all you looked at, it would be tempting for you to say left-hand rectangles are too low, right-hand rectangles are too high. But if you dig just a little bit deeper at a different type of curve, like maybe this one over here in number 2, which is increasing at a decreasing rate, let's run that same experiment. My left-hand rectangle right here, again, looks like it's too low. So left appears like it's going to be low, and the right-hand approximation right here looks like it's going to be too high. Okay, so this kind of confirms what you might have thought already from rectangle number 1. Left is going to be too low, right's going to be too high. But those are only 2 of the 4 types of curves. So let's talk about a third case here, a curve that for the first time now is decreasing. And this time, everybody, my left-hand approximation is going to look something like this, and I can see that that left-hand rectangle is going to be too high. And my right-hand approximation, probably should have been doing this in red all along, sorry, my right-hand approximation right here looks like it's going to be too low. So, interesting. This might disprove the little conjecture that we had going based off of rectangle number 1 and number 2. And let's look at a fourth case right over here. This one is decreasing but concave up. My left rectangle here, all right, looks like that. And once again, the left approximation we've come up with there is too low. The right-hand approximation, though, which will go here, here, over, and down, my right-hand approximation, I'm sorry, guys, I had that right. My left was too high yet again. And now it looks like my right-hand approximation, which I've drawn in red, is going to be too low. So let's put all this together, guys. Let's study this diagram and see what we can learn. The question right here is, what is the determining factor in whether an approximation is too high or too low? Curve 1 and curve 2 have the same result. Left is too low and right is too high. But what I want you to notice is that curves 1 and 2 have the same behavior. They are both increasing functions right here. Then, when we move on to curves 3 and 4, they have the same result as well, although it's a different result from what we came up with in 1 and 2. And what's happening with curves 3 and 4? Those curves are both decreasing. So, I'm not going to write all this out, guys, but it's just kind of an idea that I want you to have in your head. It would appear that if your curve is increasing, like 1 and 2, you're going to get this result. Left approximations are too low, right approximations are too high. But if your curves are decreasing, like 3 and 4, you're going to end up with the opposite result. Left-hand rectangles are too high, right-hand rectangles are going to be too low. So again, you can write that down if you want. It's true, but I think it's more the concept behind that that will help you if you can kind of internalize that idea. So that is what I wanted you guys to see with rectangular approximations. Let's go real quick now and let's put a bow on this by talking about trapezoidal approximations. So, What I've done here, guys, is again drawn pretty much the same four curves, 1, 2, 3, and 4, and I've gone ahead now and I've drawn trapezoids on each one of those. So let's talk about what's going on here. In curve number 1, we've got a function that is increasing, and it looks like our trapezoidal approximation right here is going to be too high. Why? Because that trapezoid is including this area right here that isn't actually below the curve. Let's move on to curve number 2 then, which is also increasing, albeit at a decreasing rate. And now it looks like in curve 2, this trapezoidal approximation is actually going to be too low. I'm missing area right there that is above my trapezoid, but below the curve. So that's interesting. When we were doing rectangles, curve 1 and 2, because they were both increasing, had the same result. But now with trapezoids, even though they're still both increasing, we have opposite results. Let's keep going, see if we can learn something else. Curve 3 is clearly decreasing. And I didn't draw this great here, guys, but in that case, ask yourself, is this approximation going to be too high or too low? This curve is going to be a little bit too low right here. So the trapezoidal approximation here is too low because I'm missing area right here that I should have been counting. Curve 4 is also one that's decreasing, and now, it looks like I'm counting area that I shouldn't be counting. So here in curve 4, I think my trapezoidal approximation is too high. Now, our friends in the science wing would tell us that right now, we have an inconclusive test right here. The behavior of the function, whether it is increasing or decreasing, does not directly predict whether your approximation is going to be too high or too low. So maybe there's another factor at work right here. Maybe there is something right here that curve 1 and curve 4 have in common, so that both of them get a result that's too high. But then maybe that curve 2 and curve 3 have something different going on that causes them to come up with an opposite result. So if we were to look at curves 1 and curve 4, what do they have in common that's different from curves 2 and 3? It is no longer a question of behavior, guys. It is now a question of concavity. It's a question of the sign of the second derivative. Curve number 1, everybody, is concave upward. And that is what led us to have a result that was too high. And the exact same thing happened right here in curve 4. Your curve is concave upward, and our result was too high. But curve 2, on the other hand, is concave downward, and that's what led to a result being too low. And the same thing seemed to happen right here in curve 3. It is concave down, and our result was too low there as well. So concavity didn't matter, you guys, when we were talking about rectangles right here. This was simply a question of behavior. Increasing or decreasing tells you everything that you need to know. But when we get to trapezoids, now behavior doesn't matter, and it's a question of concavity. So again, you can write that down if you want. It's true 100% of the time, but it's probably more important that you guys just kind of get a sense here for that feel and how to test for that on the fly. And I think that concept will stay with you better than writing down a table or a rule. All right, guys, that is a wrap on a very long section of notes on section 5.1. So let's dive into the homework, and good luck with that, everybody.